Hello, you're welcome back to our new section for our live tutorial. So in this particular live tutorial, we're going to go through limit points of a set. So this is a continuation from the point set. So we handle point sets. So we are continuing from the limit points of a set. So in our previous lessons, we took close look on neighborhoods. We took close look on neighborhoods, right? So we are going to apply neighborhoods a lot in limit points. We are going to apply neighborhoods a lot in limit points. So let's see. Okay, so to start with, what is a limit point? What do we say a limit point is? What do we say a limit point is? So a limit point is simply called accumulation point, or cluster point. So if you don't see limit point, we see accumulation point or cluster point. So let's see. If you have a line, right? If you have a line and this is representing the row number line, okay? On this row number line, I'll have maybe A and I'll have B, right? So A and B here is setting an interval. So you know that neighborhoods is simply what? Creating an interval around what? A particular center or around a particular point. So given any point, let's say 0, I'll ask you that create a neighborhood around 0. But to create a neighborhood, you need what you call a radius. Because if you are in a community, the extent to which you go create a neighborhood around you, right? So the shortest distance, you have some people around you, and the farthest you get. So in neighborhoods, we always use a very small delta, which is, we present it as delta, okay, which is the same as the radius. So assuming that you want to go to neighborhood from 0, on the row number line, you have positive and or you have left side and right side. So you have to go 2 units on the left, 2 units on the right, and that gives an interval -2, +2. Okay, so this is the concept of neighborhoods, creating an interval using what? A center and also a radius. So now let's see what a limit point of a set is talking about here. Now if you have an interval, right, an interval is having endpoints. Within the endpoint is a dense infinite number of terms you find within the interval. So within A and B, you can never list all the numbers, but when you talk about a set has a discrete element. Let's say 1, 2, 3, 4, 5. So with this 1, 2, 3, 4, 5, we realize that from 1 to 2 there is nothing in between them. Okay, that one we call it a discrete, and a set is finite. We can have an infinite set where you put 3 dots here, meaning that it's going infinity. But for every interval, we have endpoints, and that endpoint bridges or creates boundaries, and that boundaries will help us know the extent which we are going, but you can never list all the numbers between any two intervals. So what is a limit point? Now if you have any interval, as I've given you A and B, right, randomly, if I choose any member of this set, so if I have a set S, okay, a set S, which is a member of all row numbers, right, if I choose any member here, say X naught, which is also a subset or a member, okay, which is a member of what? X. So if I locate X naught here, then if I call X naught to be the limit point of the set, then I can say that if I take every, so see the condition, if I take every delta neighborhood around my point X naught, I should find at least one member aside X naught. So see, this is what I'm saying. When you have any interval AB, right, which is a set or an interval represented as S, and it's a member of all row numbers, if I locate any random member X naught within the interval, if this random number is indeed a limit point of the set, a cluster point, or a point of accumulation, Then for every delta neighborhood you choose, the word is every. So for every radius you choose around x naught, you should get at least one other member of the set. Then if you don't get it, meter is isolated. So we talk about isolated points right after. So we have limit points and what? Isolated points. So if a point is not a limit point, then it means what? It is isolated from its members. So that's the concept which I want to show you right now. So meaning that if I give you a set and I ask you to illustrate or to show if this is a limit point, I can give you an interval and I ask you find the limit point of this interval. What you do is randomly choose a number, then after take a very small delta, a very small, so a very small delta, say 0.01. You can even choose 0.001. After choosing this delta, it's expected that the interval that you form, you should get at least one of the members within it. If not, you are that particular member you choose is not a limit point. Then there are some few things you need to know about limit point, but before that, let's solve some few problems here. So let's say find the okay, now let me make it this way. Show that, so let's say show that 0 is the limit point. 0 is the limit point of the interval 0 2. So from our previous lesson, you know that when I use a square bracket, that is what? A closed interval. A closed interval, right? A square bracket indicates a closed interval. So meaning I'm giving you an interval from 0 to 2. An interval from 0 to 2. And I'm asking you to show that 0 is indeed a limit point of this interval. So if I want to basically explain interval to you, limit point to you, then it looks like it's any member of a set which is indeed close to its members. So that is the concept of limit points. So how do we tackle such a problem? So to show that indeed 0 is a limit point, then you say that if I choose any delta neighborhood of around 0, I should get an interval which will have members aside 0 in this set in it. So now I recommended 0.01 and 0.001. So let's use 0.001 or 0.01. So for delta, which is equal to 0.01, then my interval, obviously, you know that the interval is given as what? Your center C, right, minus what? Your A, comma, your center C plus what? Your A, right? So you're going to have here my center is what? 0 and my delta is what? 0.01. Sorry, this is delta, not A. Delta, right? Your radius. So I have negative 0.01 comma positive 0.01. So doing this illustrator, this gives me a new interval. So now from the new interval, we ask ourselves, do you have members of this set within this new interval? From negative 0.01 to positive 0.01. Now, as I said, for every interval, you have infinite. The word is infinite. You can't list all the members from 0 to 2 in this set. Yes, you can't list them. So what you do is, you know that somebody will start from 0, right? 0 is included because it's a closed interval. So we'll start from 0, 0.000001. Yes, this is part of this interval. So meaning that this being the small, this being very small as compared to this, meaning this is found in this interval. Therefore, using this delta, we can conclude that 0 is indeed a limit point. But now let's see, what if I choose delta 0.0001? Yes, I'll be getting what? Negative 0.0001 comma positive 0.0001. And that is also giving me an interval which I'll surely find a member of the set within aside what? Aside 0. So that should tell us that 0 is indeed a limit point of the set. So this illustration should, in summary, tell you what a limit point of a set is, right? So now let's see some brief properties of limit points here. So when you say a limit point, when it's a set, or we have some special some special sets which you have the limit points not existing and some existing. So let's see some of them here. Okay, so now one, no finite sets. No finite sets has a limit point. No finite set has a limit point. No finite set has a limit point. So now, from the illustration I made in the previous page, you know that here a limit point, we are going to find out a delta neighborhood, right? So these important terms are telling us that no finite set has a limit point. No finite set. So we ask ourselves, what is a finite set, right? We ask ourselves, what is a finite set? So a finite set is a set which is what? Having an end, right? So now, example, you have 1, 2, 3, 4, 5. Now let's see, is this finite set, here, right? Does it have a limit point? If it's true, then you say that this particular term here is wrong, right? If not, then let's see. So I'm going to assume that the limit point is, let's say, 2, right? Is 2. So once you choose 2, 2 becomes the center. Then you guess any delta, okay? And the delta should be very small. But the condition is for every, the word is every. You shouldn't choose 1 or 2 for you to confirm. But once you take a very small delta, then it means that for even the bigger ones, you surely have other members within the interval, right? So always just choose a very small interval, and you'll be good to go. So let's see. So now let me choose a delta 0.01. So that is what I recommended to you. So using 0.01, then we can have our interval, right? Let's say an open interval. You are going to have our center minus this. So 2 minus 0.01, comma 2 plus 0.01. Okay, and this is going to give us 1.99. Okay, then comma 2.001. Within this interval, can we really locate any member of this set? I mean, anything here within this interval. So let's see. I have within this interval, it's an open. Yes, it's an open interval. So we realize that for this open interval here, I can't have any member here, or you should have at least one member. So within this interval, I can have something like let's say from this set, I have 1. 1 is not part of this interval. 2 is 2 parts of this interval. Okay, so we can say that 2 be part of this interval. Yes, so we have got 1. Then now we can choose another delta, let's say a delta like a bigger delta. So let's try a bigger delta like a delta which is let's say even 4, right? Let's say a delta which is 4. So for a delta 4, we're going to have open 2 minus 4 comma hot 2 plus 4, right? And that is going to give us negative 2 comma 6, right? So for this one too, you have what some here, but choosing very small, very small. Let's say 0.00001, right? Let's see, we're gonna have an interval like when I choose a center, when I choose 2 as a limit point, I'm going to have something like 1.999 something. Okay, so the reason why we say it has no, every finite set has no limit point is that because this one is discrete, okay, the interval may not have one of them. Okay, yes, so this was a guess example, so we're going to tackle a nice one for you to understand this one. So now let's see something here. So for the second part, it says that an infinite set an infinite set may or may not have a limit point. So have in mind that every finite set doesn't have a limit point. So one thing for you to even know that a limit point is somehow like where the set of points are accumulating, but the thing is finite, so it doesn't accumulate anywhere. It's already fixed, right? But for an infinite set, it may or may not have a limit point. So now let's see a couple of infinite sets which will have and which will not have. So let's see, I have an infinite set S which is equal to, I have 1, 1 out of 2, 1 out of 3, 1 out of 4, dot dot dot. So with this set here, where is it approaching? I mean, what is it heading towards? So now what do we do? We have 1 out of 2. You realize that as the denominator keep on increasing, our value tends to approach 0. So you can say that 0 is the limit point, right? So if I take a delta neighborhood around this 0, I can have 0.001, negative 0.01, 0.001, right? So you know that this thing here, I will surely have what? I will surely have a member of this set here at all costs, right? I'll surely have a member of this set here at all costs. So for this finite set here, so I made something here which I have to correct. We know that for a point to be a limit point, after creating the interval, the point itself should not be part. We want at least any other member. So you realize that we had 1.99, we have 2.001. Only 2 can be found here, and 2 should be out before our condition be satisfied. So realize that once you take 2 out, there is no, delta you choose that you get some. Okay, so the 2 that we got wouldn't satisfy it being what a limit point. So one thing to clarify, and you know that once I take 3, I'll surely have only 3 to be part of what the set, and 3 should not be part for us to have it as a limit point. So all finite sets here doesn't have a limit point. Okay, no finite set has a limit point. So for this infinite set, as I said, will surely have a limit point because it's approaching 0, right? It's approaching 0. That is decreasing. Okay, it's decreasing, so it's approaching 0, right? So then let's see this infinite set. An infinite set like a set 2, 4, 6, 2, 4, 6, 8, 10, 12, 14, 16. You get it? This is infinite. It doesn't end. And I tell you, this will never have any limit point. If I take 4 as the limit point and I take 0.001 as my delta, I'll have what? 3.999, 4.0001. You realize that within this interval, I can only find what? 4. And 4 is actually the limit point. So excluding 4, I wouldn't have any other member here. So an infinite set may or may not have a limit point. So this particular set here has a limit point. This one doesn't have a limit point. Wow. So these are some 2 things you should know when you are dealing with what limit points. It's very, very necessary for you to take them or to take a close look at it. So now let's see. From here, let's see the concept called isolated points. Or let's take let's see isolated points. So what's an isolated point? Isolated point. So we say that a point is isolated. Yes. The word isolation means separation from what? From a group, right? Separation from a group. So once you are out of your members, or once you are separated from your members, then it means that you have been what? Isolated. Once you are separated from members, it means that you have been what? Isolated, right? So on a number line, if I have a set, let's say S is equal to, I have a special 0 here, union, an interval, 1, 2, okay? So meaning that I'll have 0 here, then I'll have what? 1, 2, okay? I'll have 0 here, and I'll have 1, 2. So the 0 here and the 1, 2, you know that 1, 2 is an interval, right? So from here to here, we do have a set of numbers here, but the 0 is what? Outside here. For us to know that it's isolated point, then here the condition is, if we take at least, if there is at least at least one delta. So you know that for limit points, every delta, but here, if there is at least one delta, that's when we find the interval, we don't get any other member of the set within, then the point is isolated. So meaning that if I say that a point, let's say 0 is isolated, when I take, even if I get one delta, right? If I take one delta, I get, an interval where I had the others. Oh, yes. But even if you get one delta, which when you find the interval, you don't see the other members, then it means it's isolated. So here the case is, you should have at least one delta, but that is for isolation, right? But for limit points, you need what? Every delta before every delta. Isolation, you need what? At least one delta. So here, even if there is one delta that when I choose, I'm not going to get other members, it means my point is isolated. So let's see. If I have 0 and I choose a delta as small as 0.01, I'll have what? 0 minus this, negative 0.01, close, open, and I have, positive, right? 0.01. So with this interval, do you think I'll get a member of this set aside 0? No, because the interval start from 1 forward, meaning that 0 is what? Isolated. 0 is isolated. But let's see something. Assuming I have chosen a delta big as 3,